Okay guys, let's begin solving Math 184, WebWork7. So, this assignment is going to be based on related rates, but we're going to talk about theory right now. I'm going to change the pens. So, before we begin the problems, let me just give you a brief on what we're going to do. Related rates, as the name suggests, we're trying to figure out the rates of different things that are related through some geometric or some imposed relationship. Okay, so the algorithm to solve for these problems will be, first of all, we're always going to find the relationship. Okay, so let's say you're given a figure or some geometrical meaning, you have to make sure that you find the relationship from it first. The second step will always be taking the derivative of that relationship that you just got with respect to time. And that's going to be defined as your rate. The notation we're going to use here, let's say you had a quantity P. You had a quantity P. The derivative of that thing would be written as dP over dt, which sometimes we, in this context, will refer to P prime. Okay, so we'll find the relationship, we'll find the derivative, and now the third step will be evaluate, which means you'll plug in the values. Evaluate the rate relation, okay, the one that you had from second part of this problem when you took the derivative. You evaluate the rate relation at the moment of analysis. Okay, I'll tell you exactly what that means. Okay, the moment of analysis is a very specific moment in time where you're trying to evaluate all these things. And that's it, that's pretty much it. The better we get at this is with problems. Let's see. So question 1 is about a ship. So I got a ship A and a ship B, where this is ship B, this is ship A. They're in my problem are 100 kilometers apart. If they're 100 kilometers apart, all you gotta do is just have a picture of that ready in front of you. Now they say ship A sailing south, so this one's going down, while this one's going up. We're given their respective speeds. Okay, we know ship A is sailing at 30 kilometers per hour, and ship B is at 15 kilometers per hour. So now, as you put this thing in motion, you'll see B is going to go up north, C is going to go south, so you're going to have those sides extended out. And now, we got to make a picture of the dynamic. So this was the initial spot where you started, okay? And now, when time passes, you'll see the dynamic change something like this, where this will still say the 100 kilometer. But this will be something, and that will be something. So that will give you the location of ship A and ship B after some time. In that some time, let's assume variables. What changed for us? The change was the position of A. So we'll say the distance that the ship traveled in that time, let's call it Y. Okay, and we're going to call the other one X, because those were the two quantities that were changing. Once you've figured out all the quantities in the situation, we need to find the relationship as the part 1 tells you. So what I'm going to do is I'm going to change the color here. We're looking for this distance, because the problem asks you how fast is the distance between them changing. So by Pythagoras, if you can see that clearly, what happens is this side here could be replicated with an x, and then this side here is just going to be 100. So now if you apply Pythagoras in the triangle that you just made with the imaginary dotted lines, what you will see is the relationship will be D is going to be equals to x plus y whole squared, well, it should be a squared here, plus 100 squared. This is by Pythagoras. Okay, so we're done with the first part. When we have a relationship between the changing quantities, x and y is changing, and because of those, d is also changing. Now, second step is to take a derivative of all of that with respect to time. So now this is probably where some people might find a little bit difficulty because they're not too used to implicit differentiation yet. But don't worry, once you start doing these problems, you'll get a hang of it. So you take a derivative of that with respect to time, you get 2d d prime. And here you'll be getting 2 times x plus y. Now because of chain rule, it's going to be x prime plus y prime. And then plus 0 for the derivative of 100. Okay, you cancel these 2's, and if you isolate for d prime, because that's what we're actually looking for, d prime will just be x plus y times x prime plus y prime divided by d. So now, what we figured out is our rate of change of d depends upon a lot of variables. We need the x value, we need the y value, we need the x prime value, we need the y prime value, and we need the d value. So what we're going to do is now come at step 3. So at step 3, we need to focus on the moment of analysis, right? If you look at the problem, what they said is, you need to start to observe what happens at 4 p.m. So at 4 p.m. and the situation started at noon, so how many hours pass by is amount of 4, right? So now we have to see what happens to the x in the 4 hours span, what happens to y, what's going to be x prime, what's going to be y prime at 4 p.m. So x represents the distance of the ship. Let me just take that back. So x represents the distance of ship B. Ship B is traveling at a speed of 15 kilometers per hour. So in 4 hours, it will travel 60 kilometers. So final eventual, this will be 60 kilometers when you're hitting 4 p.m. on the clock. Same thing with the y. When the ship was traveling at, let me just check, traveling at 30 kilometers per hour south. So after 4 hours, you're going to reach 120 kilometers. X prime represents the speed. The rate of change of x is represented by the speed of the boat. So the speed of ship B is going to be given to us to be 15. So we're going to keep that. That's not changing. Right? How about y prime? Y prime is also going to be the speed of the other boat that's given us to be this. Now, how would you figure out the d, the distance between those two ships at that point? Well, you don't know exactly how to get it, but you do have a relationship for it. The relationship we got from the previous one, where you get it by Pythagoras, you can clearly isolate for that. So that'll just be x plus y whole squared plus 100 squared square root, right? So you can isolate for that. And now to figure out d at that time, what you'll do is you'll plug in the x and y values at that time. So x is 60 kilometers, y is 120, so you get 180 in there. Right? Once we get that, we can finally evaluate the expression. So the final answer is the rate of change in distance will just be x plus y is 60 plus 120 is 180 times x prime plus y prime, that's going to be 45, and divided by d, I'm just going to keep it like that. So I'm going to keep the whole thing 180 squared plus 100 squared. And that's it. That's how you do the first problem. Let's go to the second one. So now in this case we have an oil spill from a tank spreading into a circular pattern. So I'm going to draw a circle here. They said there's the rate at which the radius is changing, so the rate where this is going out is the rate of change of area, but the rate at which the radius is going is given to us in the problem. Okay, so let's frame the argument. Let's do the first part is to find the relationship between the radius and the area, as the problem is asking us to do that. So for a circle, the relationship is just a equals to pi r squared. Second step for our analysis will be to take a derivative of this with respect to time. So we're going to get dA dt, which we're going to call a prime, equals to pi times 2r prime. Because you're going to take the derivative of r squared with respect to r first times the r prime because of implicit differentiation. So once we got that part down, now we're looking for the rate of change of area at what moment. So to figure out the moment is when the radius is 35 meters for me. So when r is 35 and r prime is not changing, is also at a constant rate, so r prime is given us to be 2 meters per second. What that gives us is that the a prime is literally just going to be pi times 2 times 35 times 2, and that's it. That's what you submit over there. Let's jump to the next problem. In this, they've already given you a relationship between these three quantities. Okay, and then they're asking us to solve for a certain value over there. Okay, they've given us the z is positive. They've given us x prime, which is dx dt, to be 4. They've given us y prime to be 6. And the moment of analysis is when x is equals to 12 and y is equals to 35. Awesome. So let's try to see that. This is exactly the same equation that we got in the very first problem here. So we have the relationship. Now let's take the derivative of that with respect to time according to the algorithm. So we get 2z z prime 2x x prime plus 2y y prime. Okay, from there when you isolate, you can cancel all these 2's after factoring it out. Z prime will just be x prime plus y prime, and you have z at the bottom. So now again, to analyze the rate of change, which is dz over dt, aka z prime, you need to have x, you need to have x prime, you need to have y, you need to have y prime, and you need to have z. We got almost all of them, we're just missing z. But we know the x and y at the moment, so we can always use the relationship to substitute back for z. Okay, from this, what you can say, z prime is x prime plus y prime over square root of x squared plus y squared, because z is literally given to us in this relationship like that. Okay, so now we can just plug it in. You plug in all the values that you have, so it's going to be 12 times 4 plus 35 times 6 square root of, going to be 12 squared plus 35 squared. Now you can submit it as it is. Alright, let's go to the next one then. So now they've given you a spotlight on the ground shining on a wall 20 meters away. So let's try to draw a picture of this. So this is the ground, and there's a building. Okay, so now we're 20 meters away from the ground. The spotlight's 20 meters away, so I'm going to label that quantity to be 20 meters. And if this is the point where my spotlight is. Okay, so that's where shining, and a woman 2 meter tall walks from the spotlight towards the building. So let's draw a stick man that represents the woman, and she's walking from the spotlight towards the building, so that's where she's going. And they've given you the speed of that. It's given out to be 0.08 meter, but we'll put it on later. We know the height of the lady is 2 meters, and we're just trying to figure out how fast is the length of her shadow on the building decreasing when she's 4 meters away. Okay, first of all, we have to make that quantity be able to, that we can easily see, right? So how do you think the shadow is going to go? We're going to take a light ray from the spotlight. It's going to just touch the head, and this right here is going to be the length of her shadow. I'm going to make a triangular diagram just to make it easier for us to analyze. So what we have eventually is just a triangle like this, where the base length is 20 meters, and then this is what we're calling S, the shadow length. Okay, let's call that S. Now the lady's right here in the middle. I'm going to represent by another line. The line's 2 meters tall because that's her height. And now we have to label some quantities that are actually happening in the dynamic way. So the shadow is changing, we know that. The other thing is changing is the distance from the building to the lady. So we're going to call that X. If the whole thing was 20, let me just put it down here so it can look much better. The whole thing is 20. And now we have the situation where we can start to analyze this. Now we need a relationship between the quantity S and the quantity X. So in this, we're going to use the tool of similar triangles. What similar triangle tells you, you got this little triangle here. Let me just change pens so you can kind of have an idea. This little triangle here is just a scaled down version of this big triangle. So we can use the proportions to kind of find the relationship. So we're going to take, let's say, this side, you would say the perpendicular side, okay, not the hypotenuse. The perpendicular of the small triangle is 2, and the perpendicular of the big triangle is going to be S. However, you got to take the ratios, right? So perpendicular to the base ratio, the base here is just going to be 20 minus X. So 2 over 20 minus X must be having the same ratio as the one for the bigger one. So the bigger one, the base is all that 20. Okay, so that's how you fix the proportions, and you kind of find the ratios using similar triangles. Now let's try to see what we're looking for. What we're looking for is the change in S. So let's make this expression so that we can only have X in there. S in there. So S will just be equals to, let me just check what I write over there at the back. 40 over 20 minus X. Okay, so now when we're looking at this, we need to figure out the derivative of this function with respect to time because we have the relationship now. So S prime is just going to be, we're going to keep the 40 outside. This is going to be negative 1 over 20 minus X squared times minus 1 times X prime. All of that because of the chain rule. Okay, so once we do that, this minus minus will just add up to make it a positive. And then, so now, once we have that expression, let me just simplify that. It's going to be 40x prime over 20 minus x whole squared. Now, at the moment of analysis, we have to see what are the quantities given to us. We need the x prime and we need the x. So we need to figure out the time when she's 4 meters away, where x is going to be 4, and now x prime is 0.08. That was given to us in the beginning. That's the speed where she's walking towards the building. Now, the quantity x in our case is decreasing as she walks towards the place, right? So little subtlety in relation rate problems is that you have to put a negative sign in front of it to represent that it's a decreasing quantity. So actual effect of x prime is going to be negative. So these meanings could be given on a different way. I can say the rate of change of x is negative 0.8 meters per second, or I can say that x is decreasing at a rate of 0.8. So when I say it's decreasing at a rate of 0.8, I incorporated the negative sign in the statement. Okay, so we're going to put that down and let's try to solve. So the s prime value is just going to be plugging in all of that thing. So you get 40 times 0.08. No, 0.8, just 0.8. My bad. Over 20 minus 4 whole squared. So we're trying to see at that moment what's going to happen. We can get the answer right away, but you'll see that I didn't put the negative. The reason why I didn't put the negative in putting this formula was because the wordings in the question are asking how fast is the length of her shadow on the building decreasing when she's 4 meters from the building. So they already incorporated the decreasing sign in their analysis. So we don't have to put one here. Even if we would put a negative sign, we'll just get a negative rate, which makes sense because shadow is going to get smaller and smaller as she approaches the building. But the idea here was to kind of like make sure the words and the statements match up. Okay? And that's it. You can plug it in. That should be the answer. Let's look at problem 5. So what they've said is a brain weight is a function of the body weight of a fish. So we have a relationship right here that's given to us. In my terms is 0.007 and w to the power 2 over 3, where w could be related to the length of a body's fish by this relationship. 0.12 L to the power of 2.53. Okay, cool. So once we have that, what do they ask us? They're asking us how fast is a species brain growing when the average length is 18. So they need a relationship between the brain weight and the length. So what we can do is we can substitute for w here and we can get to our relationship very easily. Brain is 0.07, and then all of that to the power of 2 over 3. So we'll get 0.12 L 2.53 to the power 2 over 3. Okay, so now let me just quickly calculate this quantity so that we can keep our lives easier when we're trying to do the analysis later on. Now 2.53 times 2 is going to give you 5.06. So our expression 07, so we have 0.12 to the power 2 over 3 times L to the power of, we're going to have 5.06 divided by 3. All I did is just expanded it out. So 0.12 times L to the power of that could be split up into 2 pieces. Now from this point onwards, we've got to take the derivative with respect to time and see where it goes. So b prime, all the constants in front are just going to stay there. Now I'm going to touch that. So derivative of that, where you have L to the power of 5.06 divided by 3, you're going to take that power down, so it's going to be 5.06 divided by 3 times L to the power of 5.06 divided by 3 minus 1. And of course, times L prime, because of the derivative, implicit derivative. Okay, so we got this part down. Now, what we have to see is, I have to plug in the L at the moment and the L prime at the moment to figure out the time. Well, the L at the moment is given out to be 18 centimeters for us, so we know L is 18, but figuring out the rate is not that easy yet. So L prime is something that the quantity was given in a verbal description. We have to decipher that thing and try to make sure that we get the idea. So it said, over the span of 10 million years, so 10 million years is the time, which will give you 1 times 10 to the 7 years. Okay, that's the time. 1 million years, the length grows from 15 to 20 centimeters at constant rate. When you have it at a constant rate, which means it's going to go uniformly throughout that place, right? So the rate of change of L, it could be defined as the change in L or change in time, right? So the change in L was 5 centimeters, and that happened over a span of 10 to the 7 years. So essentially you can write your L prime as 5 times 10 to the negative 7 years. Okay, once we have that whole quantity here, we can punch in all those numbers into the situation and see what's happening. So now B prime, 0.007, 0.12 to the power 2 over 3, and then we'll get 5.06 over 3, and then I'll just do the algebra for the power, so it's going to be easy for us to analyze. 5.06 minus 3 will just give you 2.06. So you'll be left with L to the power 2, not L, let's plug in the value. L was 18. 18, let me write it down nicely. 18 to the power of 2.06 over 3 times the L prime, which is 5, times 10 to the negative 7. So now you're going to get a gigantic expression out here. Okay, what I wanted you to do is, when you evaluate this expression, just that part, not the 10 to the negative 7, and see what the number is. Okay, so I'm just going to do that super quickly right now. Just give me a second. So we got 0.007 times 0.12 to the power 2 divided by 3, and then we're going to get times 5.06 divided by 3, and then on the right side what you'll get is times 18 to the power of 2.06 divided by 3, and all of that times 5 to just end up the calculation. So what I'm getting here, this number is 0.10451. Of course, you have that times 10 to the negative 7. So now what they're asking us is nanograms per year. What we got here is a mixed unit. So to convert it into nanograms, what this is going to be, you need a 10 to the negative 9. This is grams per year. So in nanograms, what this is going to be, you can move this decimal 2 places and you get 10.451 times 10 to the negative 9 grams per year. So this is just nanograms. So the answer is just that thing in the box. Okay? Let's go to question 6. Problem 6 is boat is being pulled to a dock by a rope attached to the boat, passing through a pulley. So now I'm going to be like speeding up a bit so you guys can see the idea is pretty much the same. That's the dock, that's the bow, that's the boat, that's being here, and it's being pulled at that rate. So when it's being pulled at a rate, what's going to happen is this distance between the boat is going to change. The length of the rope connecting the pulley and the bow is going to change, but this 1 meter is going to be fixed. So let's call that X, let's call that L. Let's go to the triangular diagram where we kind of figure out these quantities very easily. This is the triangle they're going to make. That's the L, that's 1. So now the relationship is pretty obvious where you can say L squared is just 1 plus X squared. Okay. Now, second step, we take a derivative of that. We get 2L L prime equals to 0 plus 2X X prime. What are we trying to look for? We're trying to look for how fast is the boat approaching the dock. That quantity in our case is going to be given by the x prime. So from this, when you isolate for x prime, what do you get? You'll get, it's going to be L prime over x. So we need the L, we need the L prime, we need the x value at that moment. Okay, so at the moment of analysis, they're giving us the rope is being pulled at that speed of 1.3 meters per second. That represents the decrease in L. Okay, so the rope's being pulled at 1.3, so we're going to put that number down there. And L is just going to be something that we have to find, where x is given it to be 8. So x prime so far is L times this, the L prime is 1.3 divided by the x, which is given at 8 meters per second for us, right? So when we're at 8 meters per second, we're trying to figure out that value. L at that moment could be given by this relationship. L could just be square root of 1 plus 8 squared, which is 65. So square root of 65 times 1.3 over 8 is the final answer for this problem. Let's go to question 7. In question 7, you have a particle moving along a curve y equals to square root of x. As a particle passes through a point 4, 2, the x coordinate is increasing at the rate of that. How fast is the distance from the particle to the origin changing? So distance from the origin for any xy coordinate is given by this relationship. Right? So at that moment when we're trying to figure out the distance, we'll use this relationship. Now the second step was to take a derivative of that. What would you get? It's going to be d prime will be 1 over 2 square root of x squared plus y squared times 2x x prime plus 2y y prime. That 2, those 2's will go away, so your d prime expression, when simplified, looks like x prime plus y prime over square root of x squared plus y squared. Now in this case, we have a lot of trouble, right? We need to figure out what's happening with certain things. We don't have any relationship for y and x, that's right here. Now we have to be able to substitute for things out of that, and I'll show you how exactly to do that. It would have been much easier if you substituted right there to begin with. So I'm going to create a parallel version of this formula where distance of the point on that curve could be given by x squared plus square root of x squared, because y is essentially square root of x. Whatever the xy point is going to be is going to lie on this curve, right? So given that, you can simplify a distance formula to be x squared plus x, and then the derivative of that must be much easier. Okay, so let's work with that one instead. In this case, the d prime will just be 1 over 2 square root of x squared plus x, and then it's going to be 2x x prime plus x prime. So now, in this context, we can easily solve for this problem, right? We need to find the moment analysis. We need to find the x prime. We need to find the x coordinate. We know it's passing through the point 4, 3 or 4, 2. So x coordinate is just going to be 4. And they figured out at that moment the rate of change of x was 3 centimeters. So x prime is 3. So we say clearly the distance prime is just going to be 2 times 4 times 3 plus 3, 2 times square root of x squared, that's 16, plus 3. No, plus 4, my bad. And that's it. That's the final answer. Now we're going to go to question 8. We have water in an inverted conical tank leaving at a rate of that much. So we're going to start to draw the picture. I have an inverted conical tank, and the water is leaving at that rate. Okay, and then we're saying it's being added at some rate. We don't know that. Let's call that quantity A. It's being added at a rate of A cubic centimeters per minute. That's leaving at that much. At the same time, what's happening is the level of the water is rising. So the water is right here. I'm going to try to draw that. The water level is changing and it's increasing. So we kind of know that the rate that's being, the water is being pumped in is higher than the rate it's leaving. That's why the water is increasing. But let's label some quantities to see what we can get out of this, right? So water being pumped in a tank at constant rate, the tank height is given out to be 12. Okay, and then the diameter of the top is 7. So I'm just going to write the radius as 3.5. Now, at the moment when you have the water, this little cone inside, the water cone, will have its own stuff here. The height will be h, the radius will be r. Okay, so we need to figure out the rate of change of this actual quantity, which is r and h, with respect to the volume, right? The relationship of the cone could be given us in the terms of volume is 1/3 pi r squared h. So that's the relationship between the quantity, right? Now, when you try to look at the argument, what they're asking you to do is they want you to isolate your stuff in just the analysis of h and volume, because they just want to figure out how the rate of change of volume depends upon rate of change of height, right? So we have to eliminate for r this equation, and this is a sidekick. Most of these problems will have always a sidekick on the exam, so make sure that you do that. So I'm going to draw this relationship here to make sure that you guys can see this. I'm going to draw this line here. So if you draw the little triangle that's happening inside, where this is the water level, if you just chop the cone in the middle, you're looking at it, you know this whole side is 12, this side we call it h, this side is r, and that side is 3.5. Using the same similar triangle ratio that we did before, we can find a relationship between r and h. So what we can say is r over h. So the perpendicular here over the base in the small triangle is the perpendicular of the long triangle over the base of the long triangle. So 3.5 over 12. So from this you can say r is just 3.5 over 12 times h. Okay? So now, once we plug it into the volume relationship, our volume relationship is going to be like pi times 3.5 12 squared times h squared times h. I expanded it out just so that we can have all the constants isolated by themselves. Pi over 3 times 3.5 over 12 squared, and then we're looking at h cubed multiplied by it, right? Awesome. So this is the expression we're going to start to work on, and now we can go ahead and take the derivative off it and see where it goes. So our v prime will just be pi over 3 times 3.5 over 12 whole squared times 3h squared times h prime. So when you have all of that, what's going to happen here is you, at the moment of analysis, you need the h prime. Okay, so trying to figure out the rate of change of volume, but we got to be very vigilant about the units in this case. The units are talking about in centimeters per centimeter cube per minute. So we have to figure out that h that we plug in must be in centimeters as well. The moment of analysis what they've gave us is the height of water needs to be in 3.5 meters. So we have to convert all these quantities into centimeters from the meters. So you saw that 3.5 was meters and 12 was meters here. We're going to convert everything into the centimeters and plug in the values that we know to figure out v prime. So when you do pi over 3, converting 3.5 into centimeters is going to be 350. Same thing bottom down there is going to be 1200 squared times 3. The h at the moment that they're asking is 3.5. So we're going to plug in 3.5, actually in centimeters, my bad. So 350 squared times h prime, and the rate of change is already given to us in 16 centimeters per minute. So that's good. We just keep it at 16. So now this right here is going to give you some quantity. That's the rate of change of volume. But we know the rate of change of volume is actually the rate that the volume is coming in minus the rate that's going out, because that's the effective rate of change, right? In the beginning of the problem, we're adding water and the water is leaving as well. So this right here must be equals to the rate of adding water minus the rate leaving the water. We assume that to be A in our analysis. So A minus the rate leaving is 7,000. We can try to analyze it. We get pi times 350 over 1200 squared times 350 squared times 16. So I'm not going to evaluate it. You can solve it yourself. And from there, you can just solve for A. That's what we're looking for exactly. A is just all of that with a plus 7,000. So we have 16 pi times 350 over 1200 squared times 350 squared plus 7,000. Okay, and that's the answer to this one. Let's go to question 8. When you look at that, water is leaking out. Well, actually, we did question 8. My bad. Hold on, there's no question 9 here? That's strange. But, man, that's okay. We'll just go skip to question 10 then. There's no question 9. Got it easy. So now in this problem, they've already given you a figure. So let me just put it down here. So that it's about a rock that's falling. So this is the place of the rock, and it falls down to ground. And then given you the quantities, a capital H, this distance is small d, this distance is going to be s, and this distance is small h. So now what we're trying to figure out is the rate of change of the shadow, which is given as s prime to us. It's all going to be symbolic here. So what we're going to do is, what they said is, first of all, they want you to call h prime v just for the analysis of the problem. So whatever we see in h prime, we're going to replace it by v. That's okay. But let's figure out a relationship here. You know it's going to be by similar triangles. So we're going to take the ratios of the small triangle. That's going to be s over h. Okay? And that must be equals to d plus s over capital H. Because we're going to take the base of the small triangle divided by the perpendicular of the small triangle. Small triangle base is s, perpendicular is h. So we do that. That happens, and then same thing for the big triangle. Base of the big triangle is d plus s, and the height is capital H. So from there, you can isolate for your expression of s. That happens to be h times d plus s times h over capital H. So you have to still isolate for s. So what we'll do is we'll just move stuff over and kind of like figure out that way. Or there's doesn't matter. You can do it anyway. There's multiple ways of isolating it. Sometimes you'll drop the d, sometimes you won't. But it's okay. I'm just gonna stick with what we got over here. Okay. So capital SH equals to HD plus small sh, which tells me when you move it over there, you get capital S factored out. H minus small h equals to HD, and then S is just HD over H minus this. It's gonna write it down nicely. Awesome. So this is the expression. On the side note, because we know that they don't want a d in the equation, so we're going to remove a d. So let's isolate for d from here, okay? In this case, just a little side note that d from this equation could be just written as s times this over that. Okay? Just out there for reference later on. Awesome. So now what we're going to do is take the derivative as we said. Now in this case, the h is changing, small h, not the capital H. Small h is changing. So keeping that in our mind, d is going to stay the constant. We're not going to change that, and not capital H is going to change. So we got to use quotient rule to be able to figure out the derivative of that expression. So S prime here will just be capital H minus H whole squared. Let me check if that was correct or not. Yeah, whole squared. Times, I'm going to keep capital H minus H here. The derivative of dH is going to be d times H prime. Minus, you're going to keep the dH as it is. And the derivative of the other expression is going to be minus H prime. So we'll replace the H primes by V as the problem asks us to do. So S prime is just going to be capital H small d V minus H d V. You have a positive H d V there, and there goes away. And you're left with this H minus H whole squared. Now, in this situation, what you got to do is you got to substitute for d, which we got in the other case to be something like that. So I'm going to say to submit the answer without the d, we'll plug in for that. So d in our case was h times, let me just double check again. Yeah, divided by h. So it's that. So when you plug it in, you get h times, we're going to keep the v outside, times s times h minus h over h all over whole squared. So what you can do is you can cancel this out, you cancel that out, and reduce this expression to be something much easier to solve and put it inside the expression. So it's going to be HVS over H times capital H minus H. So this is the answer for the first part of the problem, where you have it all in terms of capital H, V, and S. Okay. The other time of analysis is when they're asking us the speed of the shadow at the time when H and S are 0. So we're looking for S prime. We're looking for S prime here when H and S are 0. In this case, if you plug in H equals to 0 in this expression, it's not going to work because you have an H at the bottom. So you have to work your way back to something that you kind of had an idea to solve with. And we can just stop here at the expression that we had before. The S prime expression before we plugged in D was just H dV over H minus H whole square, right? So this is like the expression after you plugged in all that stuff. Now, in this situation, you can literally plug in H equals to 0, and it's not going to cause you any trouble. When plugging H equals to 0, this thing goes to 0, so your S prime is just going to be H dV over capital H squared, which could be reduced to dV by H. Okay, and that's the answer of the 10th problem. Let's go to problem number 11. We're given the manufacturing cost and revenue of a company who makes calculators. So the cost function is 70,000 plus 30x for me, and the revenue depends upon the quantity x given by 300 minus x squared divided by 20. So when the production output in 1 week is the x calculators, okay, that's good. Now if the production rate is increasing, so that's x prime. The production rate is x prime, and that's increasing at the rate of 500 calculators that we figured out. And now they want you to find when the production output is 6,000. So when x is 6,000, we need to figure out the following quantities. So the rate of change of cost, that's going to be given by C prime. So for the first part, hold on, my pen just kind of act funny. C prime is just going to be 0 plus 30x prime, right? Because if you take a derivative of that, and x prime for us was given out to be 500, so it's going to be 30 times 500. Okay, that's the answer for this one. For the B part, I want you to figure out the rate of change in revenue. Well, R prime is just negative 2x over 20. What happened to the pen? Hold on. Negative 2x over 20 times x prime. We know all of these quantities. When we put everything in, we get negative 2 times the quantity was 6,000. I think my pen's broken. Something's wrong. But yeah, I'll try to write. Times the x prime, which is given out to be 500. And this all thing by 20. Okay. So that's pretty much it. That's for those two parts. And the rate change profit. Well, profit is just revenue minus cost, right? So P prime is just going to be R prime minus C prime. So that allows us to be, from the top, you just pick up those expressions and just copy them down. So I'll just kind of like make it a bit easier for us. Negative 2 times 6,000 times 500 over 20 minus 30 times 500. And that's it. Okay, so let's look at problem 12 now. We got the relationship between price and x demand for our product. For me, the numbers are 2x squared minus 4xp plus 50p squared. And that should be equals to 22400. Now they're asking if the price is increasing at a rate of $2 per month. When the price is $20, find the rate of change of demand. So demand is represented by x. What we're going to do is just follow the steps. We know the relationship already. We're going to take a derivative of that with respect to time. So you're going to get 4x x prime minus 4 xp prime plus px prime plus 100 p prime equals to 0. So what we're looking for is the rate of change in demand. So we got to look for x prime, we got to isolate for that. So when you expand it out, we get 4x x prime negative 4 x prime negative 4 p x prime plus 100 p prime equals to 0. So when you send everything on the right side and isolate for x prime, you get, let me just do that quickly. So you have 4xp prime minus 100 p prime, everything over 4x minus 4p. Now at this point they've given us p prime to be 2 and the price itself is 20. But in order to solve for this, we need to find out the value of x because we have x over there. We have the relationship up here. We can plug in the value of p to find that. So you plug in the value of p, we get is 2x squared minus 80p, actually 80x, plus 50 times 400, so that's 20,000, equals to 22400. So when you move up everything to the left side, you get 2x squared minus 80x Now when you take it here, it becomes 2, 4, 0, 0. You factor out 2 from the whole thing, you get x squared minus 40x minus 1200 equals to 0. So now this could be factored out into, you have a 40 to be total sum, 1200 is what you're looking for. So 60 and 20 will be a good fit. X squared minus 60x plus 20x. You get, so x could be either 60 or x could be either negative 20. We're going to reject this one because that's not possible for demand to be negative. I'm going to pick this one up. So now when you're evaluating it, your x prime is just going to be 4 times, let me copy the expression down so it's easy for us. (4x minus 4p). So now we know p prime is going to be 2, p is going to be 20, and x we figured out to be 60. Punch it in. 4 times 60 times 2 minus 100 times 20 times 2, all over 4 times 60 minus 4 times 20. And you can submit that as it is. Let's move on to problem 13. In this case, they've given us a relationship between P and Q to be this: 1100. And they want to find is if revenue is dr by dt, they want you to find an expression. So first of all, revenue is price times quantity. So R prime would just be P Q prime plus Q P prime. So let's try to solve for what's happening here. Let's isolate for all the pieces from this information, right? So the equation relationship that we have is here. From this, if you isolate for P, what would you get? You get square root of 1100 minus 2q squared. And from that same expression, if you isolate for Q, you get square root of 1100 minus P squared all divided by 2. And now let's try to take a derivative of that and see what happens. So when you plug it in there, your R prime is just going to be P with a Q prime. So P is just that expression. We're going to keep it there. So it's going to be this: 1100 minus 2q squared times Q prime. So that's a derivative of this, which will be 2 square root of 1100 minus P squared times the derivative of that is going to be 2p P prime. Right? So that's the first piece. Plus, you got to keep the Q. It's 1100 minus P squared divided by 2. That's the Q part. And P prime from here is just 1 over 2 square root of 1100 minus 2q squared. And then times 4q prime. So now this expression we have a lot of math. We gotta try to simplify this a bit. Because these things are being multiplied, I can simplify that expression. Just hold on for a second. We have revenue prime equals to 1100 minus 2q squared times 2pp prime all over 4 square root of 1100 minus p squared plus all of that. So we have we gotta have a 4. That's a 4. This will go away. We'll have that square root of that q prime. Okay. The square root of minus p squared times q prime. And at the bottom, it's going to be square root of 1100 minus 2q squared. So now we want our a to just be a function of q. And then we'll have a dp dt with it, right? So in order to be able to simplify that, let's try to figure out and substitute for the things that we want to get rid of. So there's this p here. Let me just change pen so you can see that. I got to substitute for that p, but most importantly, I should be able to factor a p prime from that. In this case, there's a p prime here, so this term is okay. I got to substitute for that p as well. But this q prime that's what's going to cause trouble. But if you look at q prime that I figured out before, so if this was q, and then this piece here represents q prime. So what we can do here is simplify this expression a bit and just replace it over there. So what we'll have over there for q prime, q prime is nothing but 1/2 p prime all divided by square root of 2 times square root of 1100 minus p squared. So you can plug it in. At this point, what we have is the whole expression. I'm just going to try to write it. Times 2p prime over 4 square root of minus p squared. And then what we're going to do here, plus square root of 1100 minus p squared times q times p prime all over 1100 minus 2q squared times 2 square root of minus p squared. So now we can easily factor out a p prime from these two, and then write everything else in terms of q. One thing I want to make sure is I replace all of them. So we figured out that p is just going to be, I'm just going to write it down here on the side. So p is just a square root of 1100 minus 2q squared. So I'm going to replace those p's wherever possible and turn this expression all into that form. Now, what I want to make sure that we get is, out of this expression, if you see closely, 1100 minus 2q squared is p, and this must be the other case, right? So we're going to replace everything in that form. Oops, I'll back a bit. So now your r prime will look like, I'm going to factor the p prime already. So (1100 minus 2q squared) times 2p. So that p will just be that term, 2 times square root of 1100 minus 2q squared. And you will see, because they're being multiplied, you can simplify them further. But let's just put the whole thing down first. Divided by 4 square root of 1100 squared minus p squared. So I'm just going to replace for that p by 1100 plus 2q squared when you simplify it. So these 1100s will go away as well. The remaining part, again 1100 minus 1100 plus 2q squared times q times p, again we substitute like this. And at the bottom, two q squared, and then 100 minus p squared will just give you the same result, times 2 square root of 1100 minus 1100 plus 2q squared. That's all what a is going to be. But let's try to simplify that. So let's cancel this with that. We get 2 at the bottom. Cancel this with that. We have just 2q squared. On the top, what you're left with is just 1100 minus 2q squared. So r prime is p prime times 1100 minus 2q squared divided 2 times the square root of 2q squared. So that's this part. Plus, on that side, you'll cancel up these two. On the bottom, only these things are going to get cancelled out. That's pretty much it for the cancellation. So you'll be left with square root of 2q squared times q times square root of 1100 minus 2q squared, all divided by times 2 of that, and then this and that will just go away. Similarly here, that and that's going to go away, so this expression will just be q over 2. So what I'm going to do is I'm going to get rid of that and write it as q over 2. And that's it. We figured out this part to be our A that they wanted us to do. Second part, they want us to find the dr dt when q is supposed to be 20 and the other thing is dp dt is 4. So they given us, they want you to find dr dt, which is technically r prime, when p prime is 4 and q is 20. So with the expression that we found out before, we can use that. R prime is just going to be p prime, that's 4, times all the thing that we told before. I'm going to try to make it simplified. So it's going to be 1100 minus 2q squared, so 2 times 400, all divided by 2 times 2q squared, so that's also 400. This minus q, actually plus q over 2, 20 over 2. Yep, just checking. So this should be the answer to the last part of the problem. The last question is problem 14. So you have a water that's being poured into a swimming pool as a right circle cylinder at a constant rate. So you have a cylinder in which you're pouring in some water. The pool has a radius of 6 feet and a height of 10 feet. This is given out to be 10 feet. This radius is 6 feet. And then what is the rate of change of the height of the water when the pool depth is 8 feet? So let's try to fill in some water here. So that's the water. They say the water is going to have a height of h and a radius is always going to be the same in this case. It's going to be 6 as well. So now they wanted to find the rate of change of height when they gave us the rate of change of volume. So the volume expression here is 1 over 3. No, it's for a cylinder, it's just pi r squared h. Right? And then we know radius is fixed to be 6, so we can just write volume as 36 times pi times h. Now here you have the relationship. We got to derive this with respect to time. So you get v prime equals to 36 pi times h prime. When you have that here, all you got to need is just the h prime. They're looking for the h prime. They're giving the v prime. V prime for us is 4 cubic feet per minute. So from there you can isolate for h prime to be v prime by 36 pi. And you plug in the v prime value, you get 4 over 36 pi for the final answer here in this problem. And that's it.